Imagine you're helping a friend move.
Oh, always a fun weekend.
Right, yeah. So you pick up this huge 50-pound box of books and you carry it straight across a long, flat room.
Hmm.
Your arms are just burning, you're sweating, your heart is pounding.
Definitely doing some work.
Well, what if I told you that, according to the strict, uncompromising laws of the universe, you just did absolutely zero work?
It sounds like a total joke, but yeah, it's true.
It is. And welcome to today's deep dive. We are taking a look at a really fantastic slide deck today titled Part '04 Energy Mechanics Blueprint.
The great deck.
It really is. And our mission today is to explain the absolute basics of physics for total beginners. But we're doing it through a lens that makes it, entirely relatable for you.
Right, because physics can be incredibly abstract.
Exactly. This presentation uses this brilliant analogy throughout. It compares the laws of physics to the mechanics of physical currency.
Yeah, it takes these terrifying math equations and turns them into something you can actually visualize.
So framing it this way, it just fundamentally changes how approachable the math becomes.
It really does. I mean, treating energy as a currency. It's a currency that can be stored in a vault, spent on a transaction, or transferred between different accounts.
Like literal money.
Like money, exactly. The rules of physics are essentially the financial regulations of the physical world. So today, we're basically going to audit the universe's checkbook and see exactly how the accounting works.
Auditing the universe. Like that. Let's see how strict this auditor really is.
Very strict. Spoiler alert.
So, just looking at the first two slides of the deck here, we get the title. And then immediately on slide 2, there's this foundational definition.
Yeah, energy is the ability to do work.
Right. Energy is the ability to do work. And alongside that, it gives us the law of conservation of energy.
Which is really the bedrock of everything. It states that in a closed system, the total amount of energy remains absolutely constant.
So you can't just make it out of nowhere.
No, it cannot be created from nothing and it cannot be destroyed into nothing. It only changes forms.
Okay, so leaning into our financial analogy here.
Right. If you withdraw $100 from your savings account and move it to your checking account, you didn't magically create new money.
The total net worth is exactly the same.
Exactly. The funds just moved from one state to another. Every single joule of energy has to be accounted for.
Every single joule. Okay, so if energy is the currency, how do we actually spend it?
That's the transaction.
Right. And I'm moving over to slide 3 now, which addresses this by defining work. The slide actually says work is the transaction of energy.
It's the moment the money changes hands.
Yeah. And we get an equation here. It's W equals F times D times the cosine of theta.
Sounds complicated.
Right. Let's translate that out of textbook speak for everyone.
What these do?
The slide breaks it down as work equals the force you apply. So pushing or pulling times the displacement or the distance the object actually moves times the direction factor, which is where that cosine math comes in.
Yeah, because the universe has very strict requirements for a transaction to actually clear.
It's like having your debit card declined.
Basically, first you have to apply a force, a push or a pull. Second, there has to be a displacement. The object actually has to move.
So pushing a wall doesn't count.
Right. You could push against a solid brick wall all day until you just collapse from exhaustion. But if that wall doesn't move a millimeter, in the eyes of physics, you haven't spent any of the universe's currency.
Zero work.
Zero work.
Okay, let's unpack this because I'm looking at this efficiency gauge graphic on the slide, and I have to admit, it just feels wrong.
It trips up a lot of people.
It says if the force is applied in the exact same direction as the movement, so an angle of 0 degrees, it's 100% efficient.
Correct.
But then it shows a scenario where the force is pushing straight up at a 90-degree angle to the movement, and it says that is 0% efficient.
Yep, the math checks out.
But this goes back to my moving box example from the start.
Oh, right, the 50-pound box.
Yeah. If I am carrying a heavy box straight across a room, my arms are pushing up against gravity while I walk forward. My back and my arms are screaming. How on earth can that be zero work?
Well, it's the ultimate paradox for anyone learning physics for the first time. What you're experiencing with that heavy box is biological effort.
Biological effort.
Yeah, your body is internally doing a massive amount of work just to keep your muscle fibers contracted, pump blood, all that. You are burning calories.
I definitely am.
But strictly speaking, from the perspective of external physics on that box, you are doing zero work on the box in the horizontal direction.
That still feels like a glitch in the matrix. I'm the one moving it across the floor.
I know, but look at the direction of the force. To do work on an object, the force you apply must be in the direction of the movement, or at least have some component pointing in that direction.
Okay.
When you carry the box, you are applying an upward force just to fight gravity, but the box is moving horizontally across the floor.
Right. Upward force, horizontal movement.
Exactly. The angle between them is 90 degrees. If you punch cosine of 90 into a calculator, it gives you 0.
Wow.
You are essentially acting as a very sturdy, sweating shelf.
The sweating shelf. I love
We
that.
aren't actually transacting energy into the box to propel it forward. Its own momentum is carrying it horizontally once you get it going.
That is just mind-bending.
Hmm.
But it really highlights how strict the accounting system is.
It's ruthless.
So let's see this transaction play out in a slightly messier, real-world way. I'm moving us over to slide 4 now, which is a case study, the angled pull.
Oh, this is a great example.
We have this great visual of a little girl pulling a wagon with a baby inside. She's holding the handle,
Right.
but because she's taller than the wagon, the handle is angled upward at a 30-degree angle from the ground.
Right, so she isn't pulling perfectly horizontally, she's pulling up and forward at the exact same time.
Exactly. So let's walk through the math the slide gives us to figure out her transaction. She's pulling with 50 newtons of force. She walks for a distance of 25 meters. And the angle of the handle is 30 degrees. So using our formula, we multiply the 50 newtons times the 25 meters times the cosine of 30 degrees.
And the slide calculates the final result there.
Yeah, the work done is approximately 1,082.53 joules.
So the crucial takeaway here, which this slide illustrates beautifully, is that out of her 50 newtons of total pulling effort, only a fraction of it is actually contributing to moving the wagon forward.
Because some of it goes upward.
Exactly. The vertical part of her the part pulling straight up on the handle, is wasted effort as far as horizontal movement is concerned.
I mean, it might be lifting the front wheels off the sidewalk a tiny bit.
Right, maybe a little bit, but it's not doing the work of actually moving the wagon down the street. The
Right.
cosine of 30 degrees acts as an efficiency filter.
An efficiency filter. That makes a lot of sense.
It mathematically calculates exactly what percentage of her total force is useful for that specific transaction.
Okay, so if she successfully spends that currency and does the work, where does the money go?
It has to go somewhere.
The universe's accounting system doesn't let it just vanish. And that brings us to what the source material calls the active checking account.
Slide 5.
Yes, moving to slide 5, we enter the territory of kinetic energy. The slide defines this as the energy of motion. If a body is moving, it has kinetic energy measured in joules.
And we get a new formula here.
We do. The formula given is K equals 1/2 mv squared, so 1/2 the mass times the velocity squared.
If work is the act of making a deposit, kinetic energy is the balance sitting in your active liquid checking account. It is energy currently in use manifested visibly as speed.
I really want to pause on the notes for this formula, though, because it points out something just mind-blowing.
The squared term.
Yes, it notes that mass scales linearly. If you double the mass of an object, you double the kinetic energy.
Simple enough.
But velocity, because of that little squared symbol, scales exponentially. Let's put this in beginner-friendly, real-world terms for you.
Go for it.
If you are driving a car at 30 miles per hour, you have a certain amount of kinetic energy. If you speed up to 60 miles per hour, you aren't just twice as dangerous. You have quadrupled the kinetic energy.
That squared term on the velocity is one of the most consequential little numbers in all of physics.
It's huge.
It tells us that speed is vastly more expensive, energetically speaking, than mass. This is exactly why speed limits exist and why high-speed collisions are so devastating.
Wait, let's explore that car analogy a bit more. If I have quadrupled the kinetic energy in my checking account just by going from 30 to 60, how does that actually impact the mechanics of the car?
Well,
Like, why don't they just put bigger brakes on cars to fix that?
because the energy has to go somewhere. The universe demands its accounting be balanced.
Oh, right.
When you are moving at 60 miles per hour, your brakes have to do 4 times the amount of work to stop you as they would at 30 miles per hour.
4 times the work.
Yeah, they have to drain 4 times the energy from your checking account. Our brakes work by using friction to turn kinetic energy into heat energy.
So they get hot.
Very hot. If you generate 4 times the heat too quickly, the brake pads can literally melt or fail. The energy transformation is so violent that the hardware just can't keep up.
Wow. It completely changes how you think about pressing the gas pedal. You know,
You're taking out a massive
a
loan.
massive energetic loan every single time you accelerate. Now, what if we aren't spending the energy right now?
Then it's stored.
Exactly. I'm moving us over to slides 7 and 8, which talk about stored energy, formerly known as potential energy. If kinetic is a checking account, this is the savings account.
This is energy that has the potential to do work later, but it's currently locked up, waiting for a trigger to release it.
And the slide deck highlights two main types.
Right. The first, on slide 7, is gravitational potential energy.
The slide translates the formula for us. Energy of elevation. It relies on the object's mass, the constant pull of gravity, and how high up the object is.
Think of lifting a heavy textbook from the floor up to a high shelf. You are doing work against gravity to get it up there.
So I'm spending currency.
You are. But that work isn't lost. It's deposited into the gravitational savings account. And the slide points out a fascinating rule about this account. It is path independent.
Path independent. What does that mean?
It only depends on the initial and final elevation. It completely ignores how you got there.
Okay, let me test that. Say I have to get a massive heavy boulder up to a 10-foot platform.
Okay, a boulder?
Scenario A, I carry it straight up a vertical ladder. Scenario B, I roll it up a very long, very gradual winding ramp that also ends at that same 10-foot platform.
Mm-hmm.
Are you saying the gravitational potential energy stored in that boulder is exactly the same in both scenarios?
Yep. The universe only cares about the bottom line. You might have exerted biological effort for a much longer period of time pushing it up the ramp. And you might have used less force over a longer distance to do it, but the final energetic transaction with the universe is identical because the final height is identical. The stored energy is the same.
That's wild. Okay, then we have the second type of savings account on slide 8, elastic potential energy, the energy of deformation.
Yes.
The formula here uses the stiffness of the material and the distance it's stretched or compressed.
This is the domain of springs, rubber bands, car suspensions. The slide mentions Hooke's law,
Hooke's law.
which essentially says that the harder you stretch or compress an elastic material, the harder it fights back to return to its relaxed shape. That restoring force is what stores the energy.
The visuals on this slide make it really intuitive, actually. It shows a relaxed spring with zero energy, then a stretched spring where the force is pulling inward, and a compressed spring where the force is pushing outward. Squishing or stretching, either way, you're making a deposit into that elastic savings account.
And notice the math on the slide for this one. The distance you stretch the spring is squared, just like velocity was in the kinetic equation.
Oh, I see that.
So stretching a spring 2 inches requires 4 times the stored energy as stretching it 1 inch. It ramps up incredibly fast.
So the deck provides a great cheat sheet to keep all this straight. I'm briefly moving us to slide 9, the energy state matrix.
This is a really handy summary.
It really is. It acts as a summary of the triggers for you, the listener. Velocity triggers kinetic energy. Elevation above the baseline triggers gravitational potential energy. And deformation, like stretching or compressing, triggers elastic potential energy.
It's a perfect diagnostic tool. You just ask yourself 3 questions. Is it moving? Is it off the ground? Is it bent or stretched?
And those simple questions tell you exactly which accounts have a balance.
Exactly.
Well, we have all these accounts now. How do they actually talk to each other? That brings us to the third section of our outline, the ultimate accounting system.
Time to balance the books.
Let's pull up slide 6, which covers the work energy theorem. The slide states that the net total work done on an object is exactly equal to its change in kinetic energy. There's a phrasing at the bottom of this slide that I really, really like. It says, work is the process. Change in kinetic energy is the result.
It bridges the gap between the transaction and the checking account balance perfectly. You apply net force over a distance. That's the physical work, the process.
Okay.
The immediate, unavoidable result of that process is that the object speeds up or slows down. That's the change in kinetic energy.
So to see this whole accounting system play out in full, I'm advancing us over to slide 10, conservation of mechanical energy.
This is a classic physics scenario.
It is. We have this great visual diagram. It shows a block sitting at the very top of a steep ramp, and then another visual of it sliding down to the bottom.
This is where the sheer elegance of physics really shines. The formula on the slide says the initial kinetic energy plus the initial potential energy must perfectly equal the final kinetic energy plus the final potential energy.
Okay, let's trace the flow of funds here. At the top of the ramp, the block is just sitting there. Zero velocity, which means zero kinetic energy.
Right, nothing in checking.
But it has maximum height. So it is at 100% potential energy. Its entire net worth is sitting in the savings account.
And as it begins to slide down the ramp, it loses height but gains speed. The universe is actively transferring funds from savings into checking.
So when it reaches the bottom of the ramp, its height is 0. So the potential energy is completely gone. Where did it go?
It transformed into 100% kinetic energy. The total amount of energy never changed, it merely shifted from height to speed.
The slide actually walks us through the mathematical proof for this, and it is so satisfying to look at. It sets the starting gravitational energy equal to the final kinetic energy.
Yeah.
But because the mass of the block is on both sides of the equation, they actually cancel each other out.
Think about the implications of that. It means that whether you slide a tiny glass marble or a massive multi-ton boulder down that ramp, if we ignore air resistance and friction, they will reach the exact same speed at the bottom.
Wait, really? The mass doesn't matter. A boulder and a marble hit the exact same speed.
The mass doesn't matter at all for the final velocity. The universe's exchange rate for dropping height to gain speed is constant.
That is crazy.
Well, the boulder has vastly more energy overall because it has more mass, but the rate at which it turns its height into speed is identical to the marble.
That is wild to think about. The math just zeroes in on the final speed, giving us a clean calculation based entirely on the height of the ramp and gravity. The accounting is perfectly balanced,
Always is.
but, up until this point in the presentation, there is one massive factor we haven't even talked about.
The elephant in the room.
Yes, we've talked about force, distance, mass, and speed. But I'm moving us to slide 11. Power. The rate of transfer. We haven't mentioned time.
Time is where the human experience really intersects with textbook physics. Work and energy on their own do not care how long a process takes.
So if I'm moving a mountain,
You can move a mountain grain by grain over a million years, or you can use dynamite to blow it up in 10 seconds. The total work done, the energetic cost to move that mass, is exactly the same.
but obviously the experience is different.
Right, because the power required is vastly different.
The slide defines power as the change in work divided by the change in time. And it's measured in watts, which is defined as just 1 joule per second.
The slide also points out that power is a scalar quantity. It doesn't ask how much work was done in total, it only asks how fast the work was delivered.
The speed of the transaction.
Exactly. It's the flow rate of the currency.
Hmm.
Are you paying off your mortgage in pennies over 3 decades, or are you dropping a massive lump sum of cash all at once?
Let's make this completely concrete for everyone. Moving to slide 12, we have a case study, calculating power.
Mhm.
And this is a scenario literally everyone has experienced.
Oh, yeah, stair climbing.
Stair climbing. The slide outlines a 60-kilogram person climbing a 2-meter staircase. First, we calculate the total work done by gravity. We know from earlier that's mass times gravity times height. So 60 times 9.8 times 2. That equals 11,176 joules of work.
Notice that this 1176 joules is a fixed cost. It is the uncompromising energetic price tag that the universe demands to move a 60-kilogram mass up a 2-meter elevation.
So there's no way around it.
No, the universe doesn't offer discounts based on how tired you get. That price does not change whether you crawl, walk, or sprint. The total work is identical.
But the physical experience of walking versus sprinting upstairs is totally different. And the slide breaks down exactly why using the factor of time.
Let's look at the math for it.
Let's look at walking first. If you walk up the stairs, let's say it takes you 7 seconds. You divide the 1176 joules by 7 seconds, and you get a power output of 168 watts.
Okay, pretty reasonable.
But if you run up those same stairs, completing the climb in just 2 seconds, you divide that same 11,176 joules by 2. Now, your power output spikes to 588 watts.
So the energy expended from your account is completely identical, but the power required to run is more than triple.
That's why running up the stairs leaves you totally breathless, with your heart just pounding out of your chest. You didn't do more work.
You didn't.
You just forced your body to generate a massive surge of watts. You drained the checking account at a completely unsustainable flow rate.
Exactly. Your biological engine had to work in overdrive to provide that rapid rate of transfer. It's the difference between a slow, steady drain and a sudden, violent withdrawal from the bank.
This brings all the pieces together so perfectly. Let's pull up the final slide of the deck, slide 13, the physics of currency, a blueprint. It is this wonderfully simple flow chart that summarizes everything we've unpacked today.
It's a great visual.
Let's trace the logic one last time. On the far left, we have force and displacement.
Right. Force and displacement are the raw physical ingredients. The chart shows an arrow pointing from them, indicating that force drives work. You have to push, and the object has to move.
Then work points to energy, specifically kinetic and potential energy, which are sitting on a visual balance scale. The rule underneath says work changes energy. Energy is conserved.
The transaction modifies the accounts, but the total balance across the entire system remains perfectly balanced, just like the scale in the graphic. You can't cheat the ledger.
And finally, an arrow points from energy out to power, dividing the whole thing by time. It says power measures the speed of it all. It really is a complete blueprint.
It takes the chaotic, messy physical world around us and reduces it to a highly logical, predictable accounting ledger.
We started this deep dive looking for a beginner-friendly path through the absolute basics of physics. And this slide deck delivered exactly that by treating energy like physical currency.
It's a brilliant way to teach it.
We learned that work is the strict transaction. The exact moment force causes actual displacement. We learned about the active checking account of kinetic energy, where speed is squared and therefore incredibly dangerous and expensive.
Very expensive.
We explore the savings accounts of gravitational and elastic potential energy, patiently waiting to be unleashed. We watch the books balance perfectly on a ramp, proving that energy is never lost, only transformed.
Yep, the boulder and the marble.
And finally, we introduce the concept of time with power, realizing that it's not always about how much work you do, but how fast you demand it be done.
Exploring this blueprint leads to a pretty fascinating implication.
Oh, yeah.
Yeah, we see clearly from this slide deck that the physical universe is a strictly balanced checkbook where every action has an exact calculable cost. It raises an interesting question for you to mull over in your own daily life.
I like the sound of this.
When you get to the end of a long, stressful day and you feel completely drained, it's worth asking yourself, are you actually out of energy, out of raw jewels? Or are you just demanding way too much power by trying to do the work too fast, blowing out your internal watts?
What a fantastic way to frame it. Maybe we all just need to lower our wattage a little bit and take the stairs a bit slower.
I know I will.
Well, thank you so much for joining us on this deep dive into the energy mechanics blueprint. We hope you walk away seeing the physical world and your own energy a little bit differently. Until next time.